In this video, we're going to talk about a variety of functions that we're going to run across in our study this semester. So the first type of function that we're going to refer to is a power function. So a power function is going to be one that of the form f of x equals a times x to the m. A is some real number coefficient out in front, and m is the exponent. And what we're really going to concentrate on in these types of things is what does the m tell us about the shape of the function? Okay. All right, so the cases that we're going to worry about for the m is when m is an integer, could be positive or it could be negative, or when m is the form 1 over n, where n is some positive integer. All right, so let's start with the first case where m is a positive integer. So this graph would represent when m is 1. We'll worry about a later, okay? So this represents when m is 1. So we have f of x equals x, so we know that's the straight line, y equals x. Here is when m is 2, or y equals x squared. F of x equals x squared, so we know that's a parabola. Here's f of x equals x cubed. Here's f of x equals x to the 4th. Notice, in this case, the m's are odd in the first row. Here the m's are even in the second row. And if we keep increasing m's by 1 each time, the pattern continues. When the m is odd, let me go back to the previous slide. When the m is odd, the graph is going to go from lower left to upper right. Lower left to upper right. Okay? The only thing that's going to change is what's going on in the middle. Notice here, there wasn't any flatness at all. This is now flat at 0. It'll get even flatter if we did x to the 5th. It'll get even flatter if we did x to the 7th, and so on. All right, when we do the case when m is even, sorry about that. When we do the case when m is even, notice we decreased, got to the origin, turned around, and increased. Decrease, turn around, increase. Anytime it's even, it's going to do those same things. Okay? The only thing that's going to change again is going to get flatter in the middle and steeper on the ends. Literally, it's the only thing that's going to change as m gets larger. So really, it depends as if m is odd or m is even for the shape. All right, what happens if m is a negative integer? Well, the first case would be f of x equals 1 over x. But we know that we can't plug in 0 for x in that case because we would get undefined. So we're going to end up with this, what we refer to as a vertical asymptote here in the middle. On the upper right here, we've got this piece that's above the x-axis. Lower left here, the piece that's below the x-axis. Notice that the bigger the x gets, the smaller the y gets, because you'd be dividing by bigger and bigger numbers. So that's why it's really, really big here, because if you divide it by, say, something by 1/10, if you did 1 over 1/10, you'd get 10 out for the y. If you did 1 over 100th, you get 100 out for y. That's why this is getting bigger and bigger the closer you get to the y-axis. What if m is negative 2? Well, now both sides of that are above the x-axis. And that makes sense, because in this case you would have 1 over x squared. That's what would happen if you had m was negative 2. 1 over x squared always has to be positive. So we would expect that the graph would always be above the x-axis. Here's x to the negative 3, or 1 over x cubed. Here's x to the negative 4, or 1 over x to the negative, or 1 over x to the 4th. Notice again here we kind of got this alternating thing. The left-hand side is below the x-axis. The right-hand side is above the x-axis. So it's behaving much like what the 1 over x is behaving like. Here, both sides are above the x-axis, much like what the 1 over x squared was doing. But again, much like the previous example, notice that it's kind of here flatter in pieces and steeper in pieces. So in this case, if we're decreasing by 1 each time, making m more negative, the pattern continues like it did before. If m is odd, we'll have that negative to the left, positive to the right of the y-axis. If m is even, both sides will be above the x-axis. Okay? The only thing that changes as you get more negative is the graph is steeper near the y-axis and flatter the larger the x gets in either direction. All of these graphs, we noticed that we had that vertical asymptote of the y-axis, or the line x equals 0. It also has a horizontal asymptote, or of the x-axis, of the line y equals 0. Let me go back real quick. What we mean by the horizontal asymptote here is, here's the horizontal line, here's a horizontal line. The graph, as x gets big, the graph gets close to that line. That's what we mean by the horizontal asymptote. All of these are doing that as your x gets big in either the positive or the negative direction. Okay, let's do the case where m is 1 over n, where n is a positive integer. So this would be f of x equals x to the 1/2. N is 2 in that case. So x to the 1/2, or square root of x. So the graph would look like this. Here's x to the 1/3, or cube root of x. So your graph would look like that. X to the 1/4, or fourth root. X to the 1/5, or fifth root. So these are what we refer to as root functions. Again, notice that these graphs, when we have an even n, an even root, it's only defined on the positive real numbers. But when we have an odd root, it's defined on all real numbers. Okay? All right, so increasing by 1 each time, we notice the same pattern continues. Okay, making that denominator bigger. If n is odd, the graph goes from lower left to upper right and has a domain of all real numbers. When n is even, the graph starts at the origin and has a domain of just the positive real numbers, and it increases up to the right. And again, like I mentioned before, the only thing that happens is that n gets bigger as the graph will get steeper in the middle and flatter on the ends. What does the a do? Well, remember what the a did for quadratic functions. If a was positive, it said it opened up. If a was negative, it said it opened down. That was basically what it was. The bigger the a was in absolute value, the skinnier the graph got. The exact same thing happens for power functions. Okay? So positive means it's going to behave like the original one did. Negative means it's going to be flipped upside down. Okay? Also, they said this parabola was steeper, was narrower if the absolute value of a was greater than 1. So the bigger the a got, ignoring the sign, the skinnier it got. Flatter if it was between 0 and 1. All right, so the original one is the red one. This would be f of x equals x cubed. If we multiply by that by 2, it got skinnier. Here is f of x equals 2x cubed. Notice it just got skinnier, but it's the same basic shape. Here is the square root of x, or x to the 1/2 power. Here is negative 1/4 the square root of x. Notice in that case, it got flatter, right? Got stretched out more, right? Got smashed more towards the x-axis and flipped upside down. So here the a would have been positive because it's going the same direction, and it would have been bigger than 1. Here the a would have been negative, and the absolute value of it is less than 1 because it got flatter. Speaking of absolute value, let's talk about another absolute value. Or let's talk about the absolute value function. We define it in pieces. Remember, absolute value is distance from 0. Distance is always positive. Well, at least distance is non-negative. Distance could be 0. But it can't be negative. So what we mean by distance from 0 is that if the number is positive, that tells you how far away it is from 0. But if the number is negative, we take the opposite of it, and then you get a positive number that tells you how far away it is from 0. So the absolute value function says, leave it alone if it's positive, make it positive if it's negative. Okay? So again, like I mentioned, absolute value gives distance from 0. Absolute value is a distance function. Okay? Here's what a graph of that looks like. It says f of x equals x if x is greater than or equal to 0. Well, here's f of x equals x, right? That's just that straight line. It only matters for the absolute value function when x is positive. So that's why we stopped the graph here. Then it also says f of x equals negative x if x is negative. Well, here's the line f of x equals negative x. And again, we stopped it at 0 because it only applies if we're to the left of the y-axis, if x is negative. So the absolute value graph looks like this V shape. If we figure out what the A is doing on the outside, it has the same effect that it did for power functions. So here's your original green one. This would have been multiplying it by 4, maybe 5. I can't remember what I multiplied it by to create it. Doesn't matter. Here's multiplying it by a positive number that's bigger than 1. It got skinnier, but it stayed the same direction, if you will. Here, it got flatter. So this is a number less than 1 in absolute value. And it also must have been negative because now we flipped it below the x-axis. So this is a negative number whose absolute value is less than 1. This would have been a positive number. The A would have been a positive number whose absolute value is bigger than 1. The absolute value function is an example of a whole class of functions referred to as piecewise defined functions. So let's do an example with another piecewise defined function. Let's say we have f of x is equal to negative 2x plus 1 for all x's that are less than or equal to 1 and equal to the square root of x if x is greater than 1. This problem is asking us to evaluate the function when x is negative 3, when x is 4, and when x is 1, and then asks us to sketch it. All right, so what happens when x is equal to negative 3? Well, negative 3 is certainly less than or equal to 1, so I would plug it into the first part of the function, not the second part, because the second part only applies for when x is greater than 1. So we put negative 3 into the top part. We don't want to ever plug it into two pieces. Remember, functions have you put in one value, you get out one value. So you're never going to plug a number into two places. You have to pick correctly which place to plug it into. So in this case, negative 3 is less than or equal to 1, so we're going to plug it in the first piece. Negative 2 times negative 3 plus 1 will give us 7. F of 4, well, 4 is greater than 1, so we'll plug it into the second piece. So we'll have square root of 4, and that's equal to 2. Again, we're not going to put 4 into the first piece. It doesn't say to put it in the first piece because it says the first piece is only valid if x is less than or equal to 1. What about when it's equal to 1? When it's equal to 1, well, again, I look at my conditions. When it's equal to 1, it says put it in the first one. Put it in the first one, we get negative 2 plus 1, which gives us negative 1. Okay? It matters which one you plug it into, so be careful as far as that goes, making sure you plug it into the right piece for the restriction. All right, so to sketch this graph, we're going to basically sketch the pieces individually and then keep the pieces that we want based on the restrictions we're given. All right, so the first equation was the graph of negative 2x plus 1. That's an equation of a line, y-intercept of 0, 1, and a slope of negative 2. So you would go down 2, right 1, down 2, right 1 if we were graphing it, right? That rise over run piece. So this would be the graph of the whole line. Now again, this piece is only valid on the interval less than or equal to 1. So we'll cut that off at negative 1 and only graph the part to the left. Similarly, likewise, we're going to have the graph of the square root of x. That was one of our root functions. Again, we don't want the whole square root of x. We only want the part of the square root of x where x is greater than 1. So we'll cut that off. We'll start at 1 and go to the right. One other thing to notice, remember for the definition, it said that the first piece was valid less than or equal to 1. So we have a filled in dot at negative 1. Well, 1 negative 1, I should say, for this part of the graph because it was equal to. It actually filled in that point. Versus here, this was for x is greater than 1, so we have an open dot. Okay. Now, to get a graph of the whole piecewise defined function, we're going to take those two pieces together and put them on the same graph. So here was the graph on the left-hand part, up to 1. Here's the graph on the right-hand part for x is greater than 1.